without even a single slice of pizza to my name. Too proud to beg for change, mastering the pain. When New York niggas was calling Southern rappers lame, but then Jack and I slang. I used to get dizzy spells, hear a little rain. The voice of a...
So here's a new topic, theorem. So we have a vector field F on an open connected domain D is path independent. So this is just kind of sort of not really it's just, what am I going to say, clarifying or establishing what we've already just learned. If and only if. It's just putting it in theorem form. Let's say that. If and only if it is conservative. Okay, so this is the theorem. And then there's also two conditions. Well, not also, but that's just a separate theorem on its own. So it's just saying that a vector field on open connected domain. So open connected means that, well, I'll go over it in a couple minutes, but a vector field on an open connected domain, so that means no holes basically, is path independent, so it only depends on the endpoints, if and only if it is conservative. So like we just applied, right, in our last example. So to determine whether something is conservative or not, this is a big question, conservative or not. Okay, so what we have to do is confirm two conditions. So condition number one, that would be if you're on a simply connected domain. Simply connected domain. So basically what this part means is that you have your domain contains no holes. So if you have domain like that, that's good. Looks like a nice solid blob. But so this is good. But if you had a domain something like this, okay, that's supposed to be connected, and some like little hole in it, or like a pool, and this is your domain, you cannot have this hole in there, so that's bad. Okay, so that's not simply connected. So that's the first condition. And the second condition, so condition 2, is that all cross partials, and this comes up again, cross partials are satisfied. Okay, so in this case, cross partials again would be, I guess I'll just write them here. So we have partial f1 partial y equals partial f2 partial x, comma, and this is a new pair, partial f2 partial z equals partial f3 partial y. And the last one is comparing the last three. So partial f3 partial x must equal partial f1 partial z. Okay, so these all must be fulfilled and fulfilled/satisfied for your vector field to be conservative. So these are the two conditions for it to be conservative. Alrighty, so now on to a new topic. So I'll just open with saying that, as with everything in life, there are always exceptions. So a huge exception to what we've been talking about as far as conservative vector fields, there is the vortex vector field. So this is a major exception. So major, I'll even underline it, exception to basically all of the rules, kind of. So what this looks like, and you'll become very familiar with this, or at least you should. So the vector field, the vortex vector field, this is a two-dimensional thing. So this looks like the following. Okay, so it might look a little bit intimidating because it's actually not that simple. But anyways, this is what it looks like. So this is like our f sub 1, and this is like our f sub 2, right? So let's see, let's examine how it behaves, basically. So let's check the cross partials first. So let's check cross partials and see what it does. Cross partials. So let's do that now. So we'll do partial f1, partial y. Let's see what that is. That should equal partial f2, partial x. So let's see if that's correct. Okay, so that's the only comparison we have to do here, right? Because we don't have 3 components. So let's check that. Let's do this one first. So we'll have partial f1, partial y equals, and then we have to write everything on the bottom times derivative of the top minus derivative of the top low d high less high d low. So derivative of the bottom, so that'd be 2y. And then we have it all over the bottom squared. Okay, so this simplifies to minus x squared minus y squared plus 2y squared over x squared plus y squared, quantity squared. And this turns into a y squared minus x squared over x squared plus y squared, quantity squared. Okay, so that's that one. And now we'll do this one. So we have partial f2 over partial x. So that's going to be low d high, so that would be 1, minus high, and derivative of the bottom is 2x. And then we have x squared plus y squared on the bottom. So this turns out to be positive y squared plus an x squared minus 2x squared. So that's positive y squared minus 1x squared over the bottom. X squared plus y squared, quantity squared. So as you can see, it fulfills the cross partials condition. So yes, fulfilled. So that's good. So as of now, it looks like it's conservative, okay? But let's look at a line integral where we apply the vortex vector field. So let's start with a simple case, fairly simple case. We're going to make our curve be the unit circle, okay? So in this case, so here's our unit circle. All right, I'm trying my best to draw a little. Okay, pretend this is a unit circle. That was actually kind of good. So this is 1, 1. This is our y, and that's our x. Okay, so the parameterization for a unit circle, or just a circle in general, is r cosine theta, r sine theta. So in this case, that would be 1 cosine theta, so cosine t, actually, and then sine t, because it's just general convention that you use t as a parameter, as the parameterizing variable. So then t, to go all the way around, you have to go from t equals 0 up to 2 pi, okay? So this is our curve, and then we have our vortex vector field. Okay, so now what we have to find, this is a closed curve, right? I want to start and end at the same place. And, okay, I won't give it away, but so let's see what we get. So this is we have to plug in something like this. Okay, this is our formula for the line integral, remember? Okay, so first of all, c prime of t is going to equal negative sine t times cosine t, all right? And then we have, let's find what f of c of t is. So f, that was, well, we'll have, it was a negative y, so negative y in this case, this is x and this is our y, so negative y is now negative sine t over x squared plus y squared. So in this case, x squared plus y squared is cosine squared t plus sine squared t. And then for the second component, we had an x on top, so that would be cosine t, and that's over the same thing, x squared t plus y squared t. All right, so on the bottom, as you can see here, those are all ones on the bottom, so that's good. So this simplifies simply to the same thing as c prime of t. Okay, so we have something like that. So now we can plug it in, and our a and b are a is 0 and b is 2 pi. So if we plug it in, we get 0 to 2 pi of this thing, so negative sine t comma, cosine t, dotted with c prime of t, which happens to be the same thing. Okay, so something like that. So when you dot these, you have to multiply the first components. So we still have our same bounds. Multiply the first component, so that'd be sine squared t, and positive, right? Because we have two negatives being multiplied, plus the product of the second components, which is cosine squared t. So this, all in all, turns into a 1. Alright, so what we get is 0 to 2 pi of 1 dt, which turns out to be t as t goes from 0 up to 2 pi. So our final answer is 2 pi minus 0, which is 2 pi. So yay, that's good, right? Wait, hold on. So this is actually a closed curve, right? Because we started at t equals 0, and we went around the unit circle, and we came back all the way till t equals 2 pi. So since the start and the end are in the same place, they're the same point, shouldn't this be 0? Shouldn't the line integral all the way around be 0 for a conservative vector field? Yes, I guess the answer is yes, it should, but this shows why the vortex vector field is an exception, as I stated before, is an exception to all rules, basically. So this is an exception because it's technically not conservative, I guess. So anyways, I'll give you a little more insight into the vortex vector field. So what this is, again, here you're going to see it a lot. So minus y over x squared plus y squared, and then x over x squared plus y squared. So this is what it looks like again. And the potential function is actually, it does exist, and it is the inverse tangent of y over x. If you want to try this, go ahead, by all means. It does work out. If you take the partial of v with respect to x and then partial of v with respect to y, you'll get these two things. So what this means, though, is that and the inverse tangent of something over something, or of anything really, gives you an angle. So what that means is that the line integral is actually giving you, when you do v of q minus v of p, what this is giving you is the final angle, minus the initial angle that you were at, okay? So all in all, this actually gives you the change in angle along C, however far you traveled along your curve, okay? So as we did before in the previous example that we just did, when you do from 0 to 2 pi of the vector line integral of the vortex vector field, we just got 2 pi, right? So basically it just depends on how far you rotate your angle. So in generally speaking, on a closed curve, or maybe not even a closed curve, hold on, let me go back. When you're calculating the line integral of the vortex vector field over any kind of curve, that's just going to equal 2 pi times n. And n is, technically it's called the winding number or something like that, but n is just, I remember as number of times you circle or surround, either way, circle the origin. Okay, so I'll show you on the next slide. This will be the last concept for this video. So anyways, when, let's say you were to have something like this, right, and like a curve that we did, it doesn't have to be a perfect circle, and by no means does it have to be perfect, but let's say you have this curve, right, and you're going this way, so this encloses the origin once, right? Going around once, you just go around the origin once. You travel around it. So that would be your n equals 1, because you went once around. And then even if you go again, that just means like every trip that you make around, you're just going around the origin once on your loop. So if n equals 1, then your line integral of the vortex vector field would be 2 pi. Okay, now let's try a different one. Let's say you start here, and this is your curve. So you're going around the curve, but you don't want to go back to that point yet. So you go around some more, and you come back. Okay, so in this case, let's follow it here. So we're going this way, this way, this way. So once we get here, at this point, we already went around the origin once, a complete 360, right? And then we continue, and we're still going around, and we go around again, right? So this time we went around twice. So in this case, the line integral of the vortex vector field around this curve would be 2 pi times n, which is 2. So that would be 4 pi, okay? And now this last case, as you might or might not be expecting. So let's start here, right? And we're going on a curve, and we go around here and back, okay? So this time we're going around, going around, going around, and then so from 0 all the way to 2 pi. So here it should be 2 pi, right? But be careful, because we actually didn't even go around the origin at all. So see, the origin was here. So we didn't, this curve does not enclose the origin. So it does not enclose origin. So in this case, because the origin's not even involved, the line integral, the vector line integral of the vortex vector field around this closed curve is just going to equal 0, like normal, okay? Because the origin's not involved. All right, so this, again, this is only applicable to the vortex vector field, because that is the special case, at least in 2 dimensions. All right, so that finishes it up for this video, and good luck on homework, and I'll talk to you if you watch future videos.
Question 14, Muslim lesson 2. Dip diver, civilizer 85er. I make the devil hit his knees and say to our Father, abracadabra.